Yep.
So let's mute everybody. Hello and welcome to whoever's here, and please keep joining to the third session of our online colloquium, a Thursday colloquium, which is at a familiar time in IUCAA, which is now, as you see, in the middle of the Milky Way somewhere. And we are, this is the third session of our weekly colloquium. The plan is to actually carry this on at least for the next few weeks through the summer, and so that we have a familiar time for people to join in. And we're taking this opportunity to widen our list of normal speakers, because we can afford to have people join, like today's speaker, on the net. And then in addition to this at IUCAA, what we are trying to do now is have similar Zoom seminars at other times of the week. On Tuesdays, we have the NEAM seminar right now, which might actually be paused as from next week our annual summer school starts for undergraduates and university teachers, and a lot of people who are actually listening today might actually be participants there. During the summer school period, we will keep the day lectures on, following pretty much the same Zoom links, but there will be afternoon seminars and colloquia like today's going on. So please look out for them. So today's speaker, I'm very, very happy to welcome Axel Brandenburg, who is an old friend of ours. Axel is joining us from, it's a very different time zone, from NORDITA in Stockholm. And Axel did his PhD at the University of Helsinki, and then since then has been in various places all over the world. He was postdoctoral fellow at Cambridge, in NORDITA in Copenhagen, in Colorado Boulder, and then had faculty positions, of course, in NORDITA again, in Copenhagen, as well as in Newcastle, and has been around the world. We know Axel, of course, for his review, which he just was talking about with Kandu, which has been a very influential review in the subject, written almost 10 years ago, 15 years ago, right? And then, of course, from our faculty, Kandu has been a regular collaborator of Axel. And today we are going to learn about self-excited dynamos. We will have questions right at the end of the talk. So if you have questions, please write them down and ask them at the end instead of interrupting. It just complicates matters on Zoom. Thank you. Over to you, Axel.
Thank you very much, Somak, for your very nice introduction. And thank you to Kandu for making this arrangement here today. I'm very happy to talk to you here today. I chose to talk about the topic of self-excited dynamos. Self-excited dynamos, as opposed to dynamos that we have in some children's dynamos, where you do need some permanent magnets. So here there's no permanent magnet at all. I'm talking specifically about aspects between theory, the laboratory dynamos, and astrophysical dynamos or astrophysical reality. Let me start by some introductory remarks, in particular Cowling's theorem, which led us to the understanding that dynamos always must be three-dimensional. And this then led to the idea that most dynamos should actually be turbulent, and turbulence is generically always three-dimensional. There's also a twist to this whole story. Now, 87 years after Cowling, that is this year, that we have learned something which I find rather remarkable. So I'll come to that also toward the end. There is another connection with Kandu, of course, in addition to having written the review together with Kandu back in 2005, when I was visiting IUCAA a few years earlier, 2003. The symbol of IUCAA is a remarkable one, because it does indicate the linkage of interlocked flux rings. In fact, it's a single ring, and it crosses equally many times with a positive signature as with a negative signature. So altogether, you have a net linkage number of 0. That means in terms of magnetic fields, as has been realized by Keith Moffat back in 1969 already, this leads to a magnetic field that would have 0 helicity. This is here a picture from a paper in PhysRef E with my student at the time, Simon Candelaresi, and we advertised this IUCAA knot. So if you have never heard about an IUCAA knot, here it is. And so what happens to it in a magnetic setting is it actually unknots itself, it destroys itself in such a way that you have opposite helicities flinging off in opposite directions. You can see this here as a function of height, z, and time, that in opposite directions you see magnetic helicity going away from 0. So it's like saying you have 0 money to start with, but you turn it into a positive money, a negative money afterwards. And so you still have helicity, even though this symbol as a whole would indicate 0 linkage, 0 helicity. So more seriously now about dynamos, the idea of self-excited dynamos, and now really in the industrial setting, has its roots back in the 19th century, 1854 and onward. There were a number of different authors, Hewitt, Varley, and Siemens and Wheatstone, all of whom in the beginning of the Industrial Revolution realized the importance of a dynamo that does not rely on permanent magnets, but that can actually replace their permanent magnets by electromagnetic magnets, where the current is generated by the dynamo itself, and therefore it's a self-excited dynamo. This idea seems also a plausible idea to turn the kinetic energy, of which we have much in astrophysics, into magnetic energy. This idea was first formulated by Larmor from the Larmor radius, Sir Larmor, but and that was now 101 years ago. But soon afterwards, Cowling came up with what we now call the Cowling anti-dynamo theorem. It shows that dynamos cannot work in 2 dimensions, in axisymmetry. And so this was a big blow to the whole idea of even explaining any types of magnetic fields in astrophysics. It was only in 1958 by Herzenberg and also Backus who actually proposed what is now called an existence proof that a dynamo can actually work, at least in principle. So this was a great relief because when we had Cowling's anti-dynamo theorem, we now know that it's really just restricted to the 2 dimensions, and that's the main reason why it actually said it cannot produce magnetic fields. This was not so clear in the beginning. So people really thought maybe if it doesn't work in 2D, maybe it wouldn't work at all, maybe not in 3D either. And therefore that the magnetic fields in the sun or in the Earth and in galaxies may have completely different origins, being a primordial or some other origin. But then was another few decades, another few years later, Gene Parker from back at the time at the University of Utah, now in Chicago, who started developing what is nowadays called mean field dynamos. And this means we are working automatically with 3-dimensional magnetic fields, but we can simplify the complexity, the mathematical complexity, by averaging in a smart way, by retaining the relevant physics and making the mathematics feasible. And this was later formalized on rigorous grounds by Steenbeck, Krause, and Redler in 1966. Soon afterwards, after, in fact, the ideas of Steenbeck, Krause, and Redler made it into the rest of the Western world because they were in former GDR, which was on the behind the Iron Curtain. So it took a few years until the theory became known, and in this case, even in the inner side of the Iron Curtain, to people like Weinstein and Zeldovich, and here a paper by Rusmaikin, who then were the first to apply the same theory to galactic dynamos. Kazantsev is another important item in this list because he actually proposed something which really puts Kolmogorov theory upside down, you can almost say, because magnetic fields would automatically always be generated by any three-dimensional turbulence, even without any helicity or without any twist. And so Kolmogorov turbulence in its standard way really doesn't exist in astrophysics. And that's because in astrophysics, the medium is always highly conducting, and therefore dynamo action is a generic property of just any three-dimensional turbulence. So Cowling's the anti-dynamo theorem in modern form says, and this is here the words of the paper by Kaiser and Tilgner in 2014, an axisymmetric magnetic field cannot be generated by dynamo action under the assumption of axisymmetry of the velocity field, the electric conductivity, magnetic permeability, and the shape of the conductor. So in fact, it turns out, and I will talk about that at the end of this talk, there is a paper of this year which shows that this Cowling's anti-dynamo theorem is in fact not correct under these conditions. And in fact, you can make a dynamo that satisfies all of these conditions. I come to that at the end. But before that, we really had a period when people suffered tremendously from Cowling's anti-dynamo theorem. And the year after Cowling's anti-dynamo theorem came out, Sir Joseph Larmor wrote in his 34 paper, the theory proposed by Sir Joseph Larmor that the magnetic field of a sunspot is maintained by currents it induces in moving matter is examined and shown to be faulty. This was what Cowling wrote. No mentioning of even two-dimensionality. And it was really a fierce opposition that Larmor was facing at the time. And out of desperation, he simply concluded by saying so that if it is to be demolished, there could be no explanation of the sun's magnetic field, even remotely in sight. So, heavy words of the time. And it really, in the year 1956 here, an interesting paper by Chandrasekhar, 1956. This is after Parker's paper. Chandrasekhar proposed that the velocity, or he found that the velocity fields of a reasonable pattern and magnitude can alter the time of decay that will obtain in the absence of motions by quite large factors. So in the presence of motions, the decay can be significantly slowed down. Not a dynamo, it's a slowdown of the decay. So he is saying that, or asking the question, can the time of decay of 14,000 years in the Earth, in the absence of internal motions, be prolonged to 500,000 years, say, by velocities of reasonable magnitude and pattern? And the answer would seem to be yes, he says. And so therefore, even in the year 1956, he implicitly did not really take Parker's work seriously and thought the Earth's magnetic field could be explained by a slowdown of the decay. So he was very well aware of the work of Parker. And in fact, of course, it's very well known that the theory of Parker on the solar wind was only in the end published after Parker himself was finding himself between two very adverse referees' letters who were saying that Parker's idea of the solar wind cannot be right. And so Chandrasekhar helped him a lot because Chandrasekhar was at the time the editor of APJ already. So here Parker's early work on dynamos, here on the right-hand side, here his picture that he had, and what he is drawing is a magnetic field in the horizontal direction, which is lifted by buoyancy and then twisted by rotation. And so therefore he talks about the cyclonic motions as we know we have them on the Earth. This was the same, not only the same year, but actually the same day in the year when he also published a famous paper on the origin of sunspots, which he thought could emerge from buoyant magnetic flux loops at a depth of approximately 20 megameters that would lift and produce by magnetic buoyancy and would then pierce the surface and form a pair of sunspots, or sometimes two pairs of sunspots, as shown here. So he also understood at the time that when you have this phenomenon of cyclonic motions, you can actually solve the averaged equations, as he has done, in axisymmetry in that case, because the three-dimensionality has already been absorbed by azimuthal averaging. And he finds a solution which corresponds to a marginally excited traveling wave solution. And this traveling wave solution corresponds to exactly equatorward migration as we actually see it in the sun. Gene Parker, just this year, received for his pioneering and fundamental studies of the solar wind and magnetic fields from stellar to galactic scales the Crawford Prize in Astronomy 2020. The Crawford Days would be exactly next week. However, because of the coronavirus, they have been postponed, unfortunately. So I very much hope to see Gene Parker back in Stockholm in some of the following time to really receive this prize in person by the King of Sweden. In simple ideas, Parker's dynamo, which we nowadays call alpha omega dynamo, can be modeled and understood as the conjunction of two different processes. One is differential rotation, acting on a poloidal magnetic field. Poloidal magnetic fields, we call magnetic fields that go from one pole towards the equator or to the other pole in the meridional plane. So here you see such a magnetic field. If you have differential rotation in such a way that it is faster in the inside, and that is actually true only in the very near surface layers of the sun, as we nowadays know, then such a magnetic field would be twisted in such a way that it would be put into the plane, which is in the phi direction, and therefore would lead to a positive phi direction, phi magnetic field, azimuthal magnetic field, up here in the opposite direction at this high latitude. This is here a face-on view. And now you have another process which is involving cyclonic convection of a buoyant magnetic flux tube. This effect is nowadays often referred to as the alpha effect. Alpha is the first letter in the Greek alphabet, and it was simply just a coefficient at the time, but it's now also called the alpha effect. If you have, and this is exactly Parker's idea, such a toroidal magnetic field which you lift upward, then it will be exposed to the effects of the expansion in a stratified medium. So the motion will be expanding, and therefore it will, and you have this Foucault pendulum effect in your building, of course, it will be exposed to the rotation of the global rotation of the body. And that means it will be tilted in a clockwise sense. And that means you will now have a poloidal magnetic field again from this toroidal magnetic field, which points again in the clockwise direction, as you see here, and the anti-clockwise direction up here. If you compare this loop with this loop, you see they are similar, but this one have a similar orientation, but this one is shifted by a certain fraction towards the equator, and at the same time, a new loop has emerged at high latitudes. And so you see, therefore, the possibility of explaining the equatorward migration, provided this entire system is self-excited. So this, of course, then depends exactly on the magnitude of the alpha effect and the differentiation, and the effect of turbulence, because turbulence leads to turbulent diffusion. And this alpha effect, which is also a turbulent effect, has to be strong enough. So one really has to solve the equations, and one has to have reliable estimates for the alpha coefficient. And that was, of course, what Parker was already for the first time doing, and then subsequently this was worked out by Steenbeck, Krause, and Redler. Here we see a magnetogram of the sun. We see the cyclic magnetic field. The magnetic field of the radial component of the magnetic field is changing sign, negative, positive, and this has also the opposite orientation in the southern hemisphere. This is manifested also through the emergence of bipolar regions. Here we see a positive and a negative sign. Again, positive, negative sign. Always the positive sign is leading in the northern hemisphere. Here the negative sign is leading. So we have an indication of an underlying toroidal magnetic field with a systematic orientation that is opposite in the southern hemisphere. We understand this dynamo, as I already alluded to, as a conjunction of two effects. One is the differential rotation, which we call the omega effect. It produces from a poloidal magnetic field a toroidal magnetic field. And then this toroidal magnetic field, through the cyclonic events, can lead again to a poloidal magnetic field by tilting these bipolar regions, which is called the alpha effect. I should point out that not all dynamos are of that type. In fact, we know of a number of other dynamos. One of them is called an alpha squared dynamo, where even the omega effect is replaced by an alpha effect. That is in principle possible. I will not really talk about that here today. I will briefly mention yet another possibility, namely that you can have dynamos where there is no connection between poloidal and toroidal or Bx and By at all. And each of them can grow separately on their own. And that is possible if you have a turbulent diffusivity that is not only negative in the relevant wave number ranges, but also negative enough to overcome the molecular diffusivity to make a dynamo separately for each or any one of the two components. And then finally, and you notice here, in all those cases, use an overbar. An overbar means that I'm talking not about the actual magnetic field, but about the average magnetic field, which for many purposes is simply an azimuthal average. But this does not even always need to be the case, and this is already what I alluded to at the very end, namely this axisymmetric dynamo of this 2020 paper earlier this year, which actually does produce a magnetic dynamo with just the actual magnetic field based on differential rotation and on a anisotropic but axisymmetric conductivity. So that's the closing of that dynamo loop in that case. So I'll come to that later. So you remember, even Chandrasekhar at the time didn't really take Parker's work seriously, perhaps. And it was only in the work through Steenbeck, Krause, and Redler and many other papers by this group in Jena at the time, in former East Germany, that worked with the azimuthally averaged or statistically averaged electromotive force, U cross B. And so the fluctuations, which is a residual of the mean of the velocity V prime and the magnetic field B prime, they calculated. And it turned out that it actually has a component parallel to the magnetic field itself. It also has a component parallel to the curl of the magnetic field, and that corresponds to the current density, and therefore turbulence leads to an enhancement of the turbulent diffusivity. But it actually leads to a new term as well, alpha. And they even worked out how big this alpha term is. It is related to the velocity dotted into its curl. And that is what we call the kinetic helicity. Kinetic helicity is something that is not always present. In the Earth, for example, it would be present because of cyclonic motions. It would have opposite signs in northern and southern hemispheres. So it's not something that you would get when the entire world is mirror symmetric. It does require violation of mirror symmetry. And here's the turbulent diffusivity. So the paper of Parker, 1955, received only a few citations in the first decade, and really it took off significantly in subsequent years. And this was approximately the time when Kandu and I wrote our review, not that it has to anything connected with that, but it really hit a time when many of the people in the world became able to simulate and find automatically the effect of dynamo action and large-scale dynamo action in their simulations. So it is really a topic that has not stopped being of major interest to the astrophysical community. But it also marked the end of a remarkable generation, because important people in the field, these are all people that I'm very close to, or was very close to. Ed Spiegel, for example, did important work in the 80s on the magnetic activity variations and solar luminosity variations. It died in New York 2020, in 2nd of January this year. And I'm very sad because I was hoping to still finish a paper with him. In particular, Karl-Heinz Redler of the important paper of Steenbeck-Krause-Redler also died earlier this year, and even David Moss. All of them, I'm very grateful for their mentoring efforts and their mentoring, which really have affected significantly my personal career. How can a dynamo work in principle? So I mentioned already the importance of 3 dimensions, the 3rd dimension, and this becomes evident by this simple cartoon picture, which really illustrates that you can actually amplify the magnetic field in a ring, in an axisymmetric ring here, by 4 different processes. The first one is stretching, so that keeps the magnetic flux unchanged, but it makes the dimensions larger, the length of dimension larger, but the cross sections smaller. Then you twist it into an 8-shaped figure, and you fold it back onto itself. Both of these processes require the 3rd dimension. And then you have to have a tiny bit of magnetic diffusion. And in fact, we don't know of any dynamo that still works for 0 magnetic diffusivity. In the perfect conductor limit, or not in the perfect conductor limit, but in the perfect conductor case, we don't know of a dynamo that actually works. The limit is something else. The limit means it's the magnetic diffusion is still there, but it's extremely small. That is okay. But if you put it to 0 from the very beginning, as is often done in many magnetohydrodynamic numerical codes used in astrophysics, that in principle cannot work. Meanwhile, we also know of a number of dynamos that also work in laboratory experiments. We don't have a successful dynamo yet that works with plasmas, but we have dynamos that work with liquids, electrically conducting liquids, of which there are 3. There's sodium, there's mercury, and there's the 4th one, which I now forget, which is the cheaper one. No, it's also very expensive, but it's not so dangerous. Mercury, of course, is dangerous or poisonous, and even mercury and even sodium is dangerous because it can burn. But here's a dynamo experiment done in Karlsruhe, and it really follows very much the idea of Karl-Heinz Redler and also Fritz Butze at the time of a flow that is that has the swirl intrinsically in it, in very small motions, in very small dimensions. And you see here, there is a tunnel which has impellers. Impellers are internal blades on the periphery of the channel, which puts the flow in swirling motion. And it has the same orientation on every single channel, regardless of whether the flow goes up or down. You have always the same sense of swirl. And so altogether you have these 52 so-called flow diverters. The flow is pumped back each time. There's a bit of a boundary effect, which makes everything not exactly homogeneous, but other than that, it is basically a homogeneous dynamo. And it actually was shown to work in very much the same way as is actually expected based on mean field theory. There was another experiment done in Cadarache where one is still experimenting and trying to get the ITER project underway. But they also have a lot of liquid sodium around, and they also did an experiment over back in, sorry, not 99, but 2007, which works also with helical motions, but on a more macroscopic scale by having what is often referred to as the French washing machine, having opposite orientation of two different propellers on the two different sides, which sets the entire flow in between into a rather turbulent flow, but a turbulent flow that has some net helicity. And it actually was successful back in 2007, which led to a FISREF letter paper. In general, dynamos work by turning kinetic energy into magnetic energy, or in more complete sense, thermal energy in the astrophysical cases, which has its origin again from nuclear fusion and surface cooling at the surface. That leads to the dissipation of kinetic energy into of thermal energy into kinetic energy under certain circumstances if the system is really unstable, really benign unstable. That means it leads to convective motions, and that is a question of how big the opacity is. So in certain stars, you can have outer convection zones, and they would lead to kinetic motions. And it's only these kinetic motions then that can divert some of the energy, which is not being directly turned into a viscous heat, into magnetic heat and energy. And it is this energy then that can lead to the magnetic field, provided we also have some dynamo instability, so that this channel can actually be activated. It does not always have to be activated. In situations of axisymmetry that I mentioned already, where Cowling's theorem applies, this may be a problem. Here's a proof of an animation of a Herzenberg dynamo, which indeed is also three-dimensional. It works with two cylinders, but the cylinders are at oblique angles relative to each other, which are different from 90 degrees and 180 degrees, or 0 degrees. In between, you can have actually dynamo action. This was shown in an asymptotic analysis. When I emphasize the word asymptotic analysis, I should emphasize at the same time that there is no analytic solution to an actual dynamo until earlier this year. So the dynamo that I will talk about and mention at the very end is in fact an example of an axisymmetric dynamo that violates Cowling's theorem, and it actually the solution can be obtained in closed form analytically, and it's actually confirmed numerically. So the MHD equations are essentially equations of magnetohydrodynamics, velocity field, which leads to an electromotive force, and it's this electromotive force which can lead to the generation of magnetic fields. You see that this velocity field only enters in this place. And so therefore, there is a possibility of also, alternatively, considering a much simpler mathematical treatment of what is known as a kinematic dynamo, where one really doesn't bother solving this equation and ignores the feedback, which should be okay if the magnetic field is weak, and if you ask the question whether a magnetic field can be self-excited. So that's the kinematic dynamo problem that, in particular, this last thing I will mention is taking advantage of. So I mentioned already three-dimensional turbulence. Here are many such examples that have been obtained in modern numerical experiments. Here we see an energy spectrum. Let me stop this spectrum. What is shown here is the magnetic energy and kinetic energy, magnetic energy in red, kinetic energy in black, as a function of wave numbers. Large length scales here, so very little energy at large length scales at intermediate times. there is maximum energy at some intermediate scale, and we do have scale separation. That means we have enough separation between the forcing scale, energy injection scale, and the system of the size of the system. And then as time goes on, the magnetic field changes. It's completely random at early times, corresponding to this time here. But then you see that in the early stage, when the feedback is still very subdominant and begins to become important only now, roughly, you can already have magnetic fields that is strong at a scale somewhat larger than the forcing scale, but not as large as a system scale yet. So everything is still random. There's no net orientation here. And you see that larger and larger eddies develop, corresponding to approximately this time here. And then at very late times, the system changes the magnetic field changes its shape, its form, and becomes subject to the boundary conditions, which in this case is a periodic box in a cube, satisfying periodic boundary conditions. If you do the same experiment in a sphere, and here not exactly the same experiment, but an experiment in a spherical geometry, but with convective driving, you see here that magnetic fields can be strong in lower latitudes. They are strong around some equatorial belt. These are simulations here by Patrick Capula, Marit Mantere, and myself of 2012. You see that as time goes on, this blue belt begins to move a little bit further down towards the equator, and a new belt of positive magnetic field, opposite orientation, emerges and propagates also equatorward. So this is something that looks at the surface of it very much like what we know of a solar dynamo. There's many other such dynamos. I will not go through all of them. Shear dynamos and convective dynamos, and supernova-driven dynamos, they all show magnetic field generation. So the spectrum that I just explained is very similar, regardless of whether we talk about a large-scale dynamo and a small-scale dynamo, if we are talking about high wave numbers. In both of these cases, you can typically have a slight super-equipartition of the magnetic energy M over the kinetic energy E at small length scales. But at large length scales, you have can have a very significant dominance of the magnetic energy, the red line, over the kinetic energy. So we have something that we generate order out of disorder. The system was in principle completely disordered to begin with, and even at intermediate times, and it really only achieved its order at late times in this fashion, for example. And so this is basically what I explained. It basically, so the spectra and the movie, and it fits roughly the prescription, the pictorial explanation of Parker, of having a flux tube that you lift and twist. And that is what we call the alpha effect. There is a number of, I mentioned that in the beginning, a number of different dynamos that can operate, and that are not always of the type that actually involves helicity. In fact, already Glenn Roberts, not Paul Roberts, but Glenn Roberts of the year 72, had a series of not just one flow, which was helical, but 3 other flows, all of which were non-helical. And all of them generate not only a magnetic field and are therefore generating a dynamo, but they actually generate a large-scale magnetic field. Is magnetic field on the scale larger than the forcing scale, or the scale of the intrinsic scale of the flow, whose wave number is k0. So all these flows have the same x and y velocity, but a different uz velocity. So these 3 flows are all non-helical. Let me orient myself here. Because I do have here a question to you. And the question is, what would these dynamos actually be if they are no longer helical? They cannot be an alpha effect dynamo. They must be something else. And so there is altogether 5 possibilities that I allow you here, multiple choice. And you have the possibility, and if Somak can give the rest of you advice on how to do that, please unmute your microphone and let us know.
Okay, so what we are doing here is we are taking a poll, and the poll is actually in the chat window. I want all the people who are listening here to go to the chat window. You can click on chat on below, the chat window will appear. And there's a link that Surud has posted on the chat window. It's a Google form. If you click on that, you have 20 seconds from now to choose A, B, C, D, or E. Look at what these options are. And then at the end, we'll tell you what the poll result is. So we'll wait for 20 seconds from now.
So it's either an alpha square dynamo, alpha omega dynamo, which does require shear, a beta dynamo, which requires negative turbulent diffusivity, a gamma effect dynamo, which requires pumping, or a small scale dynamo that I also mentioned. We could call it an epsilon effect dynamo.
No, please don't write the answer in the chat window. Go to the Google form and click one, because we will get it all together.
Okay,
Some
so you have
people are actually putting the answer in the chat window. We can't tally there.
So you see the answers and will let us know. Let me give some explanations here. So the Roberts 4 dynamo, the last one of the 4, actually is one that works with negative turbulent diffusivity. It's therefore a beta effect dynamo. How is it possible? It is possible by because a negative diffusivity, you would think, leads to a blow up of the magnetic field at all possible length scales. And in fact, this is not really true.
We'll stop the, sorry, Axel, we just stopping the Google form now, okay?
Yes, in fact, those of you who now answered this one may not be, that's not the only answer, in fact, it turned out. So don't give up or don't be frustrated if you, especially if you're now in the last second, put negative diffusion here as the answer.
Can I stop you and ask Surut to declare the result?
You want to say something, or what do you?
Yeah, sure. So we have C, which gets the most votes. It is about 50% of people.
Oh, good.
Say C.
And who are the others? A, B, C, D. How much have they got? Give me the results for all.
A is like 10%. B is 19%. Then D is 14%, and E is 14%.
But C wins with 50%. So Axel.
So D 50%, you say?
No, C is 50%.
Yeah. And D has how many percentage? Interesting.
D is 14%.
Did anybody have D? So I said already, D.
D is 14%.
D, yes, 15%.
Okay, good. So the possibility of a beta effect dynamo is in fact a possibility. So we know from certain methods that allow us to determine numerically now, using what is known as a test field method, the diffusivity. But it turns out to be a quantity that is wave number dependent. And so only on small wave numbers, that means large length scales, is it actually negative. So it's shown here on a logarithmic representation, and it has a negative part, and it's independent of k in this wave number range. Then for higher wave numbers, it turns out to be positive. So this is simply the numerically obtained answer for this particular flow. However, there's 2 other flows, namely the Roberts flows 2 and 3. How should those work? It turned out that in those cases, the turbulent diffusivity is positive, and it can therefore not be a beta effect dynamo. So we must look for something else. And it turns out that in these cases, the solution is actually time dependent and migrating. So it's a traveling wave where you can have traveling waves that propagate in opposite directions for Bx and By, one particular type of, for Roberts flow 2, and in the same direction for Roberts flow 3. And they become stronger because the dynamo is excited. So this is a dynamo that works with the pumping, and the pumping effect is not a turbulent diffusion effect, which goes proportional to the wave number squared, but it's actually linear in the wave number, and with an imaginary part. And so in the absence of any time delay or any memory effect, which leads to an extra imaginary part, this dynamo would never lead to self-excitation. But because of the memory effect, there can be a contribution to the imaginary part, which then leads to a real part together with this I, and can make the dynamo supercritical if this part is bigger than this one. And so therefore, the answer D has in fact also been correct for the Roberts flows 2 and 3. So now let me come to the final step, namely the axisymmetric dynamo that was published in a paper by Franck Plougnan and Thierry Albusier in 2020. It was the first demonstration of an axisymmetric dynamo. However, it does require an anisotropic conductivity. Nevertheless, it is axisymmetric. There's nothing depending on the azimuthal angle. So they have a conductivity tensor that just depends on a certain angle, which is around 30 degrees for the best case scenario. It must not be 0 or 90, but it's independent. It's a constant in our geometry here. And so you just have off-diagonal components to the conductivity tensor. What is the significance of an off-diagonal component? It is quite significant because if you now think of the usual dynamo loop here on the left, you see that you have a poloidal field, or BR. You can turn that into azimuthal field by the omega effect. And in fact, we are thinking here of a cylinder that is rotating, and it's even a rigidly rotating cylinder, which is quite easily manufactured in the laboratory, especially because you don't even need liquid sodium. You can do it with copper. So you just take copper, embed it into another big copper steel block, and made in conducting motion with lubricating mercury in between, for example. So that's possible with rigid rotation, but you do have differential rotation because you have the change between, an abrupt change between the cylinder and the copper block outside the cylinder in the experimental verification. So that generates from any seed poloidal field a toroidal magnetic field. And that then, again, because of the off-diagonal conductivity, which has a component in the phi direction or phi r direction, it would operate on the radial current. The current is the curl of B, so a B phi, because of a z dependence and axial coordinates, generates you a radial current, and this radial current can then produce, because of this component of conductivity, an azimuthal vector potential, and its curl again, its axis, this azimuthal vector potential can generate and thus imply a radial magnetic field. And so it closes this dynamo circle again. This is how the dynamo works. It's a remarkable piece, which of course I found hard to believe. There could be something wrong. He gave a talk yesterday, a Zoom talk with us yesterday, and there were immediately questions by people. Maybe there is something not right with your jump in the velocity field. So here's, for example, how the conductor looks like. It is, in this case, it does, in fact, in this case, have, technically speaking, a non-axisymmetric design, in the sense that in order to have a conductivity that is different in the, or is strong in this spiraling direction, you have done it here by having many different layers of conducting copper in between insulating material. So the design, the technical design in their particular case does in fact involve non-axis symmetry. However, that's not the case in the mathematical and numerical simulation, of which is shown the result here. So these are results obtained with a pencil code by Matthias Reinhardt and myself just recently. So we are convinced there's no problem with this dynamo whatsoever. Before closing, let me tell you what my take on the coronavirus is. I actually think that instead of having this exponential growth that everybody is talking about, you actually have predominantly a quadratic growth. In the early days, in the first 30 days, it was the square root of the number of cases and the number of fatalities that increased linearly in time to a remarkable precision. This has changed in the meantime, but there is an idea that I put forward that allows you to understand this. If you had, and that's why I call it peripheral growth, if you had everybody in the infected region already being either contained or isolated from the rest, and so they would not have exponential growth in the region anymore, you could still have growth only on the periphery of people who are traveling away, diffusing into some other region. So their number is proportional only to the square root of the number of people in the interior. So therefore, this number, if you integrate this differential equation, leads to a growth that is proportional to time squared. And this is very well obeyed by this law here. In recent, this is details of this you find in an archive paper here. If nowadays, however, the curve has changed, it became flatter, and I think this is after China took very significant measures to confine the virus within Wuhan and China. It has then spread out through the rest of the world, and now much of the world is also taking confinement efforts, various ones, and they have been doing this already all along. And you have never seen at any time exponential growth, except perhaps for this very short intermediate period. So it's always a piecewise quadratic growth. We now believe that there's actually some systematic reason for that. You can understand this by having the famous SIR model, S for the susceptible, I for the infected, which grow exponentially depending on how many susceptibles you have, and recovering people. But you do need the spatial extent. And so here I'll show you the numerical simulation of this. Let me see. Yes, you see the number of infections is growing here. And that corresponds to China. And my zoom is so now you have seen the end of the movie. So now this is the infected people in the other part of the world, which started to grow later. My movie is a little bit slow here. Maybe it now in the second round works a little bit faster. So you have first China growing, then you have everybody in Europe and in the US in this simple model, which is solved also with a pencil code. Of course, it grows like this. And the solutions then indeed show a piecewise quadratic growth. First the slope like this, and later on the slope like this, very much like what is observed. So let me conclude. Dynamos work in axisymmetry. They, of course, more generally work always because of turbulence, and so you can treat it in ways involving mean field electrodynamics. Not all of the dynamos are axis symmetric, and not all of them involve helicity. Regarding the coronavirus, let me say I believe actually in what is called piecewise quadratic growth, which is observed, which I think I can explain in terms of local region where the number of people who are infected has already saturated, either by many people becoming immune, which is not an impossible idea either, herd immunity it's called, or by, simply as a consequence of the very tremendous confinement efforts. But they still lead to a quadratic growth. And we see that throughout the rest of the world. But it was at no time ever exponential. Thank you very much for your attention. And I'm happy to take on questions.
Thank you very much, Axel. It's a great way you combined your dynamo talk with the COVID bit at the end. We have quite a lot of people here who can ask questions. If you've seen how we conduct this, normally we would ask you to keep all your audio muted, but if you go to the participants window on the right, you will find a way of raising your hand. If you have a question, please raise your hand. I'll let you ask the question one by one. So can you please do that? Can you use the raise hand option to ask the question? Are there any questions from anybody?
Not even on the coronavirus. Maybe I confused everybody.
Either for the dynamo or the coronavirus. A lot of people participated in the poll. Indulekha has a question.
Yes, please.
Comment on the flipping of the magnetic poles of the Earth.
The flipping of the poles of the Earth. So the Earth's reversal happens in a pretty irregular fashion. It happens, but the time intervals have been shown to be chaotic. So they are not regular. It's not like a cycle, not even approximately a cycle. It's really pretty much chaotic. And so you have basically something like a step function. The pole is pretty much locked onto one of the geometric poles. Either the magnetic pole is either close to the geographic north or the geographic south. It can flip. But it's not very far away from the geographic pole. And then all of a sudden comes a time when the magnetic field becomes weaker because of changes perhaps in the nature of the chaos. So the dynamo in the Earth, in the outer mantle, in the outer core, which is a liquid iron, is also a turbulent dynamo, but on a much, much longer time scale. The turnover times are thousands of years. And so the dynamo is turbulent and chaotic, but it very much locks onto one polarity at a time. And it's only when you have significant disturbances in the turbulence, rare events, say, that you can have a reversal, and then it flops. So it's a pretty random and chaotic flipping. So I think there's studies of fractal dimensions of the attractor and stuff. But in fact, the details of the dynamo are all subject to numerical simulations. There are the simulations by Paul Roberts and Glatzmeyer of the 90s, and many of the modern simulations are all very similar to their early simulations of the dynamo. And they seem to be in many ways more or less realistic. There's a number of extra effects involving, for example, the core mantle, the coupling with the inner solid iron core, for example, and stuff like that. Does this answer your question? Or are there specific things that you were after?
Just one doubt, actually. You said only with a strong disturbance can the flip be there.
Right.
But the disturbance is going to affect the turbulence. So where does this fact that it will flip come in?
So the dipole moment can in principle orient itself in any of the directions. Suppose, for example, and it's being aligned mostly through the effects of differential rotation. But if the turbulent effects, which are generating and dissipating effects both at the same time, are strong compared to the differential rotation, it can operate in any direction. It can flip the magnetic pole. It makes the overall field weaker. This makes it easier for the field to revert, and then it can flip. That's what we have seen in the simulations of dynamos. I mentioned that their simulations are in many ways fairly realistic, but they are also not very accurate as a predictive model at the moment, because flippings occur too often. They occur in the simulations more often than actually in reality. So I think one can be open to questioning exactly the mechanism behind it. As I said, it does involve also coupling with the inner solid core. So it's not a very straightforward mechanism that one can easily believe and appreciate by just looking at animations of it or pictures.
Thank you very much. We have Pratik Sharma asking a question after this.
Hi, Axel. Very nice talk. So I had a question about this anisotropic conductivity part that you mentioned. So this anisotropic conductivity is turbulent conductivity, right? Or microscopic conductivity. This is microscopic.
It is actually microscopic.
In the case of copper, yeah, but in reality, how would it,
yes.
in an astrophysical situation?
So in an astrophysical situation, what you could imagine is a anisotropy by the magnetic field itself. And
that's
in that case,
okay. That's like a plasma physics, like a Brzezinski type.
That would be a plasma physics dynamo.
Okay.
This has not been proven yet. We have actually started simulations with that. So we have implemented this. It's a fairly straightforward implementation because you have an electromotive force just proportional to J multiplied by B. So it's J times B, but in the direction of B.
Mm-hmm. So will this generate small scale fields, because the Larmor radius?
We would hope it would generate large scale magnetic fields that are axisymmetric.
Okay.
So we are doing these simulations in axisymmetry only at the moment.
Mm-hmm.
We are only able to obtain, in this case, an axisymmetric magnetic field. It's either successful or it's not. In the case of their prescribed conductivity, it is successful. Our very first experiments, naive experiments, let's say, have been unsuccessful so far. But it's too early to give up on that because there's no rigorous proof that such a nonlinear dynamo should not work. It's a vast parameter space that we have to explore.
I see, sure. So I had a very quick question on your coronavirus thing, because I could not stop myself from asking it. How good is the approximation of diffusion for humans have really long mean-free paths, even in presence of containment or whatever, there are people delivering food and whatnot, like they're leaving one place to other. So won't all this be, how seriously can you take this modeling is my question.
Right. That's, of course, a good question. I did estimate, so this diffusive growth is the simplest thing you can think of, first of all.
Sure.
If you think of an evolutionary system, you put a diffusion term, and that's what Murray and many other people in biology have been doing. I did estimate the kappa, and it turns out to be really huge. And I'm not sure whether I should believe that. I forget the exact value. But of course, the coronavirus has in fact also spread quite rapidly.
That's
so
right.
I think this we should think of this diffusion as not necessarily only just geometric diffusion. It could actually also be diffusion along a sociological tree.
Sure.
There's only particular connections that work.
There are hierarchies in this,
hierarchies and stuff. Yes.
Okay.
And then in addition, you would have some element of randomness. And so I'm thinking of adding also a forcing term at some point. Other people have done that also, but not in a spatially resolved system. And that can then model, of course, the effect of an airplane traveler.
Okay,
movie.
Thank you.
Thank you.
Thanks. So we had another question that's vanished. Next is Shiva Kumar.
Hello.
Go ahead.
Sir, good evening, Axel.
Yes.
My question is, in the motion from small scales to large scales, in any of the structure formations, why is in the dynamo models reconnection not a discussion at all?
So you're talking about structure formation in the early universe?
No. In the dynamo models also. So
yes.
You start at a small scale and evolve into a large scale, right?
Yes.
In the magnetic field, when it is evolving, can you imagine without reconnection the evolution of the magnetic field?
Oh, I see. So you're asking whether something like the inverse cascade,
not only inverse cascade, anything that is forming from small scales to large scales, does it not involve magnetic reconnection? Why is it not discussed at all?
It does involve reconnection.
Yeah.
It does always involve reconnection. I said already, a dynamo without any diffusion would not work.
Mm-hmm.
It is a question that is somewhat controversial in some sense, or at least to a lot of controversy when you discuss with people, because some people don't exactly understand what we mean by the ideal case. So by the ideal case, we really mean that people write b by dt is equal to curl of u cross b. And that's it, no diffusion term whatsoever. That cannot be correct. There must be a diffusion term.
Mm-hmm.
And the nature of what they do, if they don't do the physical diffusion, if they do some numerical diffusion only, it depends then on the nature of this numerical diffusion. That we have also actually shown. There's an earlier paper of this year on that particular feature. But I don't know whether I answered really your question now.
No. Why is magnetic reconnection inherently a part of the discussion in dynamos? So let me put it that way. Although diffusivity is there,
yes,
from small scales to large scale development, there should be reconnection at all scales, right? Why is it not studied?
Why is it not what?
Why is it not studied or discussed?
Why is it not studied? So reconnection is something that is in the MHD framework, basically the same thing as magnetic diffusion. Okay. However, reconnection does take particularly important roles in dilute plasmas. Okay. So, for example, in the solar corona, I do have work of last year with Matthias Rempel on this aspect, and so we have actually found some significant effects in the case when the plasma is dilute. The magnetic Prandtl number is then large, and what we actually find is that most of the energy, which is first turned from kinetic energy to magnetic energy, actually then gets turned back into kinetic energy and is not being dissipated as diffusion or as magnetic as ohmic heating. And this is quite remarkable in the sense that people who are thinking of heating the solar corona, they think usually in terms of current sheets and ohmic diffusion. Diffusivity times current squared. No, this is not actually the answer, because the magnetic Prandtl number is large. Most of the energy gets turned back from magnetic energy into kinetic energy and is then being dissipated viscously. And that has been also confirmed by many numerical simulations. So you refer you to that recent paper where this aspect has been studied. We are also studying at the moment fully collisionless plasma dynamos. Again, I didn't have time to talk about that. We have a paper that we hope we get through first draft letters when resubmitting now, where we actually show that dynamos suffer significantly from Landau damping. This is an effect that has not been considered in collisionless dynamos as yet. And those dynamos would be relevant to, for example, clusters of galaxies, where the mean free path is extremely long. So that's my answer regarding reconnection. So in dilute plasma.
Thanks. Can we move on to the next question?
Thank you.
I mean, if Shivkumar has other things you can ask, maybe send an email.
Yeah, thank you.
Thank you. We have maybe we'll have the last question. There's another hand up, Gaurav Goswami. Go ahead. Gaurav, go ahead.
Yeah, I have a question regarding the COVID model. So yes. In these SIR equations, so if I don't introduce the diffusion term and I just let my lambda depend on time. Let's say it's a step down function such that it simulates lockdowns, right? Because if you don't have lockdowns, then lambda has some value. But once you introduce all the mitigation measures, lambda will have a smaller value. That's the transmission coefficient. I mean, this is the contact rate, right? So do you think that would capture the same things as your diffusion term?
So what I actually think instead is there is some extra effect that decreases S, and not just lambda. I mean, lambda indeed can be dependent on time, but also depending on space. But also the diffusion itself, kappa, can depend on space. It could be, for example, different outside the city of Wuhan, for example, or something like that. Again, these are cases that I have not examined, but this is all conceivable. The reason why this, again, can be important in some regimes is because it is this diffusivity that, together with the growth rate, determines the speed of outward front propagation. Right. So therefore, that is important. But I basically see the S, the number of susceptible people, as another important thing that actually we basically have reduced due to the lockdown. If you ask the virus, why don't you infect anybody else anymore? The reason is not because the virus cannot spread enough or grow enough, but because it doesn't find any susceptible people, you could say. And this could be either because the people are locked up, or the people are simply immune and already, right. Which may in fact be the case. I mean, in the city of Stockholm, we have quite a fraction of deaths of the order of at least 0.5%. And now we don't know, is the rest already immune, or, I mean, there's a lot of freedom in Stockholm, as you know. And it is bad, but it's not that bad, at least for much of us. But much of us are also locked up, of course.
So actually,
voluntarily.
I should just mention that the reason I asked this is because we had a web paper, I mean, I with some of my collaborators, where we are trying to extract the time dependence of lambda from the data, but not for SIR, for SEIR model.
Yes.
And there, I think we get some kind of step down kind of behavior but we do it for individual countries. But I think one should also think about what happens globally rather than, I think that might be.
But if you actually look at the actual data, shouldn't you be impressed by the fact how clearly it is quadratic growth?
Right. So that's why this is like the data for the entire world, right?
That's the total fatalities here.
Right.
Throughout all of the world. And the latest data point is of this morning.
Right.
So I think if I ask myself, can this quadratic growth here be just by chance? Right. I find this very hard to believe. I think it is really there must be something more to that, and namely that just it is a perfectly quadratic growth, not something like a 2.2 or some other kind of exponent. No, it's always 2, amazingly, but the slope is simply different. And that depends on the number of hotspots. So if you remember this movie here, in the beginning we had one hotspot, and then we had the small growth corresponding just to the hotspot in China. Then we have many other ones: Italy, Spain, France, then the US. And the US really began to have a saturation only very, very, very late, around the 15th or 17th of April. And then the curve begins to affect it because the number of these hotspots simply decreases now. So I find that an interesting proposal, and this is completely new, and it should simply be checked by a one-to-one comparison with the actual demographic data. Which, of course,
I think this is very interesting.
Yes.
Okay, thank you.
Great, thank you. I think there are no more questions, so we'd leave today. Well, thank you very much for the speaker, and thank you very much for the participants and your questions. The only way to applaud on Zoom is that if you go down to reactions, there is a applaud button that you can press. Otherwise, let's thank again the speaker for wonderful talk and the lovely questions and answers. Thank you.
Thank you very much, Shamak. I very much enjoyed this opportunity. I very much enjoyed the company and the opportunity.
Great to have you with us. And once things get relaxed, we look forward to seeing you again.
Yes, in person, and really see the interlocked flux ring again.
Thank you.
Thanks, Axel.
Thank you, Kandu. It was great. It's great seeing you.